So, hello everyone, this is Abri, and I will be showing you the aspects of the microstructure module and microstructure as a particular, discussing all about the physics of the microstructure evolution in typically in the additive manufacturing process itself. So I will be sharing my screen now. So I will be discussing about the simulation of the aspect of the microstructure evolution, typically in the laser powder bed fusion process. However, uh, in Paanduv applications, we are doing not just the microstructure, we are covering the entire process workflow of the laser powder bed fusion process itself. Starting with the process illustration, as you may all know that how the laser powder bed fusion works, it basically allows the layer-wise deposition of the metal powders in a sequence-wise manner, and then you have the typical melt pool dynamics that occurs. I hope the previous session has already covered that aspect. And then after the solidification, there comes the evolution of the microstructure, which is the most essential component in the material's performance and the part quality itself. After the microstructure generation, what we can have is we can have an idea about how the material can perform by considering certain classical equations that are quite trivial in the material science. And herein we have like different sorts of strengthening mechanisms that we will be considering. Coming to the overall dynamics of the process, the microstructure evolution depends largely on the temperature gradients and the solidification rate. In case of the additive manufacturing process, the microstructure has been observed quite unique in comparison to that of the conventionally manufactured components. Such type of microstructure is observed typically. Consists of the structures that are typically observed in forging, typically observed in the casting, all are combined together. Therefore, in additive manufacturing, it has been a common term to describe the microstructure as a heterogeneous microstructure. From this, we can see that after the formation of the microstructure, we have the microstructure looks much like a welded microstructure, like a weldment structure, you can say. And from that weldment structure, if we use them higher magnified microscopes, we can have the subgrain morphologies, which is the columnar and the cellular sort of microstructure. From this portion of the graph, you can also see that what are the exact conditions for the formation of the columnar, equiaxed, and the cellular microstructure, which is generally operated in the additive manufacturing process. As a progression of the microstructural study, I would like to bring about the topics that will show you the microstructure progression in terms of the different length scales. Basically, if we are intending to design a component, and in our case, I am considering for this study, we are considering the aerospace industry, and typically for the aerospace components, additive manufacturing are being recently utilized quite effectively. So we can see here, let's say I am designing the part of a gas turbine blade. In the gas turbine blade, it is subjected to particular high elevated temperature regimes and also dynamic loading. Therefore, that material has to have a enhanced creep and fatigue resistance. Typically, the material that is used for this purpose is Inconel, that is a nickel-based superalloys that has been introduced quite a long time now and has been effectively used for aerospace-based applications because it has got different sorts of strengthening, specifically at high temperatures. That is the different precipitates that occur at elevated temperature conditions. So we can see, we start up with the SEM-based characterizations, and also with the SEM we have the EBSD to get us the grain morphology. And with that, what we can see here that extending to that, we have the correlative microscopy. In the correlative microscopy, we have TEM-based analysis, and also apart from that, we have atom probe tomography. Combining with all these characterizations, we have the phase diagram analysis so that the material compositions can be tailored accordingly. So based on these considerations, what we have is the complete description of the material, that is whether this material will be suitable for that part application or not. So here is a practical scenario that I am demonstrating based on the some of the data that I have collected so far, and in that I am showing you the data for the SS316L alloy, which is quite trivial in additively manufactured, specifically in the laser powder bed fusion. So what we have is a heterogeneous microstructure consisting of the cellular, dendritic, and the columnar microstructure all together in a same in a single material. Even though the material is a single phase material, it only contains the FCC, phase centered austenite phase. Also, we have the grain morphology that can be tailored with the alteration of the process parameters. So process parameters are something that is governing the microstructure evolution in the additive manufacturing process. Other than that, another aspect of study is the surface defects and the subsurface defects. In that, what we have is and to study that, we have different microscopy techniques that is trivially used, that is the EBSD and TEM, EBSD and TEM based studies, specifically with the high resolutions. And that's how we can study the unique microstructure of laser powder bed fusion. Now I would like to explore the grain evolution aspect. In this, well, this is a pretty much short session. So in that I will be showing that how the grain evolution in additive manufacturing process is actually occurring. In the melt pool, or that is during the melting process, there is a formation of melt pool. During the solidification process, and additive manufacturing being a rapid solidification process, it allows the grains to nucleate quite preferentially faster in as compared to that of the other manufacturing processes. The nucleation and grain growth is primarily favored by the temperature and the temperature gradient itself. The higher solidification rate in combination with the temperature gradient allows the formation of different morphologies of the grain. That is, whether it will be a columnar grain or the equiax grain is primarily dictated by the different sorts of combinations of G by R ratio. That's how it is defined in the literatures. So different G by R ratios are resulting in the different grain morphologies, and G cross R, which is basically the rate of solidification, governs how the grain formation or which sort of grain morphology is a predominant one. Another aspect in additive manufactured components is the crystallographic texture, that is the preferential growth along a certain direction. In this crystallographic texture, but it is observed that the thermodynamically favorable directions are always favored for the grain growth. Typically in the cubic materials, that direction will be 001. So in general, if you are printing any component in the laser powder bed fusion process, it is observed that for without, if you are not considering any change of the scan direction or anything, the typical grain growth direction will be 001, or along the build direction is parallel to the 001 crystallographic direction based on this Miller indices. Also, we have the energy density that is actually tailoring the grain morphology and also the crystallographic texture in certain cases. However, the scan paths or different scan strategies are more dominant in that respect. That is, if we change the different thermal histories, it will result in different microstructure and specifically different grain growth directions. The energy density is in powder bed fusion is expressed in terms of power to the volumetric mass that is we are considering for the movement. That volume is described as a rate of volume is measured in terms of the considering the scan speed, hat spacing, and layer thickness. That is the entire melt volume that is actually propagating or experiencing that laser power. That's how it is expressed. It is the energy flux, you can say, or let's say the energy input that is actually bringing out the change in the microstructure evolution. Coming to that, to correlate all those things, I would like to wrap this particular physics of microstructure evolution as being a rapid solidification phenomena. It allows heterogeneity in the microstructure. It also considers the thermal cycles, that is, the process itself has a melting and remelting cycle, which we generally call as the intrinsic annealing cycles, and also the material chemistry. Since the rapid solidification the doesn't actually cover the you can say the solute segregations, and the constitutional segregation is the most common thing that is observed in the additively manufactured components. These solute segregations often act for the give you the additional strengthening in certain materials, and these are dependent upon the chemistry of the material particularly. Also, like the preferential crystallographic texture, crystallographic texture also affects the material strength of the component, and also based on the directional, because different directions have different strengths. Crystallographic directions have different crystallography, because most dense packed planes have more slip planes in compared to that of the other directions. Also, the formation of the intrinsic defects. The intrinsic defects contains the dense dislocation network, which is one of the most trivial observations that has been made for the additive manufacturing process. The dense dislocation network makes it provides an additional strengthening to the material. So, coming to the modeling aspect. So the modeling aspect, if I consider the microstructure evolution, should consider the thermal field data from the CFD based simulations, or which we commonly called as the melt-pool dynamic simulations. Thermophysical properties like diffusivity, viscosity also aids in the development of the accurate models, because diffusivity gives you the spread and the viscosity will gives you the determine the how much heat will be dissipated throughout the particular pool. Coming to the including the considering the thermal conductivity, that will dictate about the melt pool geometry, that is the depth and depth of penetration that is generally governed, and the trivial equations like Rosenthal that will dictate whether the geometrical parameters how they are dependent on the temperature field. To model the microstructure has been a critical aspect since its inception. Modeling a microstructure constitutes of several assumptions, and these assumptions are often inaccurate in certain terms, considering all the aspects, that is length scale, considering the chemical segregations, considering the crystallographic growth, considering the heterogeneity. All these aspects are not captured in a single go. These are some of the misunderstandings that has been there, that if you are modeling the microstructure, you are covering it all. It's quite difficult. It's a challenging for converting it to every model. So it is not at all possible. So there are certain popular models that we can see here, that is the Monte Carlo Potts models, cellular automata, and phase field modeling. Based on different length scales, these modelings have different fidelities that actually contribute to the computational cost or the computational time that has to be there. Several instrumentations are needed for the microstructural study, which can be pretty much expensive in certain cases. These instruments are oftenly the high-end electron microscopes, typically SEMs, TEMs, atom probe tomography, and also to justify whether for the part qualification sort of things, we need to go for the densification measurements, which is generally given by the micro CT based data. We have synchrotron based studies for the melt pool dynamics. Typically the melt pool dynamics, it's very hard to capture, specifically in the you need to have X-ray imaging and these sorts of advanced techniques, and these facilities are quite rare. This is me who has worked with the FIB and sampling, and that's how we have the like sort of making the lamella for the TEM and working on it. Another aspect that is there, to have a three-dimensional EBSD, to have a quantified data for both the cases. Let's say we are having some deformation sort of thing, and we need to know what will be the deformation bands, and we need to capture all that. Let's say deformation twins, and we need to capture that in the three-dimensional space, which is quite difficult to do that. In that, aiding to that, a software would be a better tool that can replace the huge spectrum of instrumentation in the studies. So these are some of the challenges that I have already discussed, that data acquisition is difficult, needs space, time, in situ monitoring requires high-end facilities, it is a cost intensive, time intensive, and also it requires skills to operate these sort of experimentations. Simulation is, you can say, one of the predominant solutions that we can think of. That is, we can simulate it before we print it. That's simple as that, so that we can engineer the n number of process parameters, and so that we can reduce the number of trials. And if you reduce the number of trials, you can get rid of the n number of samples, get rid of the number of tests. That's what we can do. We can solve different governing equations from the CFD and FEM approaches, and we can go for the Monte Carlo based simulations, so that we can have the heterogeneity, we can capture the heterogeneity of the microstructure. Talking about integrated computational microstructure engineering, I will say that there are certain aspects in that, that is the multi-scale and multi-physics approach. So the simulation that you should have, it should have a physics informed approach, because without the physics informed approach, you are lacking the accuracy of the model. Typically, for at Paanduv applications, what we do, we have different modules already about the powder spreading, about the microstructure, about the melt pool dynamics, which they capture quite efficiently, where we are capturing the melt pool, the particle dynamics is captured efficiently using the DEM approach, and the thermal and fluid aspects, that is a computational fluid dynamics, is a predominant tool to capture the thermal and the fluid distributions, considering the Marangoni, which the previous session has already, I hope the previous session have already captured all these phenomena. Coming to the microstructure module, this is an interesting module wherein we have performed we have taken different models. So in our case, what we have done to capture the heterogeneity in the microstructure, we opt for the Monte Carlo Potts model. In the Monte Carlo Potts model, we cover the length scale that is up to the EBSD level, and we can generate all sorts of things, including if we are coupling that data with the thermal and fluid data from the thermal fields from the CFD data. So combining these two informations, we can get the accurate microstructure. So the microstructure evolution that I am going to represent is that some of the important features we can see here, that the microstructure evolution in the PravaH gives you that not only the spatial but as well as the temporal variation. Like I have told you in the previous slides, that having a three-dimensional microstructure in an actual scenario is a very difficult thing. With an aid of a software, what you can do, you can take up the entire microstructure, have a temporal and spatial resolutions, and you can take out different time intervals wherein you can get different morphologies of the microstructure that has evolved with different time intervals. Extending to that, we have a crystallographic data that we have plotted based on the different misorientation angles. Other than that, we have a 3D tomographic information that we can use based on our ease. To get at the perfect melt pool geometry, we considered the data directly imported from the thermal field data directly imported from the CFD. So these are some of the trivial informations that we can capture. You can clearly see here that along the build direction, that different frames, it's a SS316L structure, and you can see it is efficiently capturing the columnar epitaxial grains as well, that sustains its same crystallographic orientation along the melt pool along different melt pool boundaries. So apart from that, we can also see that there are different grain size distributions. We can see this distribution seem quite similar to that of the similar to that of the um, bimodal distribution sort of thing, and the grain size distribution is there. And the temperature field that we have used, the model that we have used is basically based dependent on the Rosenthal's equation that correlates the geometrical parameters with the temperature field parameters. That's how we. So the nucleation and the CD is very probabilistic, that because we are using kinetic Monte Carlo approach, that is allowing you. This is the only method where you are allowing the different nucleation paths or different nucleation areas, and it allows and then with temperature or the energy conditions, that is a free energy boundary conditions, it will allow the grains to grow along a certain crystallographic direction. Another data I would like to present, this work is done by our team at Paanduv Applications, and we can see here that how a single spot can be mimicked using, we can not only just covering the single layer, we can see here the entire melt pool dynamics that is happening. That is the how the melt pool data is coupled with the microstructure data. So we can see how efficiently the thermal conditions are captured, how efficiently the four phase physics is captured. That is the vapor phase and the shielding gas is already there in the simulation. That is the interaction of the vapor phase and the shielding gas is also captured quite efficiently. And the microstructure that you can see here is developed like this. So basically we have a high fidelity melt pool dynamics model. We have the temperature field, that is the dynamic temperature field and the solidification fields. We take that data and extend that with them, coupled with the Monte Carlo based nucleation and growth approach, and with that we evolve the we go for the microstructure evolution. So that's how we have the, following the 4 steps, you can have the exact microstructure that you generally see with the EBSD process. This slide actually shows the physics behind the melt pool evolution with the modeling approach. So I'm not going to the details of it. You can check it, that how the grain boundary minimization and reorientation probability is considered, so that the grain growth, it can switch, or you can say different grain orientations can be arranged based on the temperature conditions, because it's a function of temperature. So that's how it is performed in the, it is like the background of the software. So for our considerations, I am running for a case study that is based on the Inconel 718 microstructure evolution in additive manufacturing process. I am considering Inconel 718 because it's a standard aerospace material, and this software PravaH is really useful, not just for the melt pool dynamics and the microstructure. It can also extend that up to the part qualification purposes as well, because before you make that part, you can already run these simulations and you understand the physics, and based on these physics informed models, you can have a better idea or a better approach to innovate the material, to have a justified model that can tell you about that can actually predict about the microstructure, about the evolution with time. So we will be covering all these aspects here. So the approach that I will be following, the same, that is the 2 previous, that is the high fidelity melt pool dynamics and the dynamic temperature and solidification fields, are already captured in the previous session. I will be capturing the Monte Carlo POTS model simulations, that is the simulation of the microstructure, and talk in detail about the microstructure evolution, what is actually happening behind the software. So coming to the hands-on tutorials, so I will present you with the hands-on tutorial, and in the tutorial I will be covering the how to load the thermophysical properties, and that will be dictating the material properties that we are expecting for that particular material. We will load the scan patterns, that is we can customize the scan pattern based on our need. That's what we can do in PravaH. We just need to make a CSV file and we can import it, and you can just have it, because all these simulations that I have shown previously has different sorts of different sorts of scan strategies. So and also it's a multi-layer, multi-track simulations that takes some computation time, of course, but apart from that, we can also run for the demonstration purposes. I will be running it for a single track, single layer model. We can choose the fidelity based on the computation time. Again, because the fidelity in mPrava, we have a tool that controls the fidelity of the process. We will run the microstructure simulations, and I will show you how you can do the post simulation processing. That is the how you can like you can navigate the entire software, you can render it, you can show it, and how you can take different spatial and temporal aspects of the microstructure itself. And then we will analyze it and extend our analysis based on that. So get ready for this. Want to explore new materials, and you just need to follow the steps. Once you do, just revisit it. That's the ease of a simulation process, and that's how I'll be presenting. So then next couple of minutes, I will be showing you the microstructure module with mPrava. So let's say we are creating a new project that is, let's say, micro test. I'm sure you have already familiarized with the software because the GUI is pretty simple, and I'm sure that you know how to create a file, and you can navigate it pretty easily. It's very simple. So create new, select a directory. Let's say I am selecting documents. Let's make it here. Let's make it.
Abardeep, can you minimize the background tabs for better visibility?
Which one are you saying?
The background, the PPT.
Sure. So let's say I'm putting it here in the Additive micro. I prepared it already. Save it in here, and the file is already created. I hope some students are already doing it simultaneously. Then you press the microstructure button.
Sir?
Yeah.
Is this a new project, or do we have to have the old loaded project already for microstructure?
Well, no, you don't need to load the project. You can do that. I will show you that as well. I am just demonstrating you that how you can create a new file and how you can explore it for a new material as well. Like let's say I want to do the simulation for Inconel 718, and how Inconel 718 being a standard material, how I can use our GUI and can present this. Are you getting my point?
Yes, sir.
Yep. So please follow the steps that I will be doing. So select this microstructure tab, move your cursor to the settings. You can see here there are several areas, which includes the alloy properties. The alloy properties considers several informations, which type of alloy and what is their temperature. And you can change the alloy by having a drop down list that we are providing with the software. It's a Inconel 718. So we select it, and then you have the entire properties. You can do reset. You can see the solidus temperature. So we can see the solidus temperature, thermal gradient diffusivity, and you can also have the other parameters, which is the process parameters, I think the solidus temperature is a problem, so let's put it for Inconel. It is 1527. You can make these modifications as well, like I am doing. And okay, let's perform the. We can have the. Other than that, we have the process parameters. These process parameters, and the process parameters we can have uh, the preheat bed temperature that is we generally keep. So let's keep it at 373 Kelvin, that is at 100 degrees centigrade. We can keep it. The laser scan speed, it I am considering is around let's say okay, let's say the laser scan speed will be 0.96. The laser power being 285. I recall these values from a paper, by the way. So, and the D4 sigma values, I will be giving D4 sigma 10, 1, 1 E minus 5. Yes, that will do. And yeah, the layer thickness and other things will be all right. I will be adjusting the fidelity. So I will be adjusting the fidelity to 20%, let's say, and it will be 10. Sorry, and yeah, we apart from that we have simulation preferences, which actually gives these are the these are the simulation parameters basically. So in case of the grains, we have something called spin states. They are actually covering the, or you can say they are taking part of the crystallites. So these spin states actually change based on the Monte Carlo based model. And with these width and depth adjusting parameters, we have what we have is the width and depth adjustment parameters that we generally do for the calibration purpose for the first timers material that we are doing. And um, so apart from that, we have process parameters and different process parameters. We have the laser power, scan speed, and and D4 sigma spot diameter. We have the layer thickness that we define in meters, and we have substrate height that we need to give. Also, we have the alloy heat absorption fraction that would be generally typically within the these values are generally taken based on our uh, based on our observations that we can see with the number of trials, because it is not specific for different materials. Apart from that, we have a parallelization, another capability of PravaH. That is, if you have the higher number of cores, it will be the lesser computation time, so the computational costs can be typically minimized. So this can be the case that I would like all of you to try. This is a part of your assignment problem. That if you remember in the previous session, what he has demonstrated, what Dr. Chabalwal has demonstrated, what he has demonstrated is a effect of different process parameters. So this is the case one from that, and that's how you can load, and you save those parameters using this, and done. And you just go back, save all, considering all the changes, then just press on the run solver. Of course, it will take some time, and you can take the launch console and you can see the process is going on, and using the show results you can directly do that. This will take a while, and I believe are you guys already navigating through, and I mean are you guys already in the same page where I am currently showing?
Hello, sir. Is my voice audible?
Yep, you are audible.
Sir, I am on the same page, but there is one thing that I would like to, consider that in the previous session as well, you don't consider absorptivity of laser beam.
Yeah, they do. They have different Fresnel coefficients and absorption coefficients that you need to take as an input for the macro scale simulations at for the LPBF. It is there already.
Well, I didn't see, maybe I didn't see, but I don't think you have used absorptivity in case of
It
Gaussian
is
distribution.
no, it is there. It is there. It is there. You may
Okay.
have missed it, but Even I think I can show you here around. I mean, it's process is already running. Well, I can terminate the process as well. So it is there. Let me check where it is. So you see, these are the Fresnel coefficients, that is basically taking care of the optical aspects, that is the interaction of the laser and the powder particles. So basically we are not just assuming the laser as a single wave or anything, we are considering it as a discrete particles. That is, each laser particle is interacting with the powder particles. That's how we um, simulate the interprocess. And for the absorption, let me check. For the absorption, it is there. It is, yeah. So this is particularly where you can tailor the laser profiles. And in the macro scale module, there is something called absorption coefficient. Yeah, here it is. Did you follow me?
Yes, sir. Yes, sir. Yes, sir.
Yep. So yeah, you see, we are taking it. So well, we are pretty much considering all the aspects. So yeah, you can simulate it. We are considering all those aspects. It's possible that you may have missed it, but yeah, that's all right. Yep. So we can see here. Well, it's running. Where is that? So you see 40% progress. So it will take a while. I think we are having some time constraints already. I believe I can load load the similar case that is already there. You can be with me, and I will be uh, I will be loading another uh, text so that I can cover the in next session as well. It will be taking a while. Yeah. So I am closing Emperor for now. Can do the save and terminate, and you can close that, and let's.
Meanwhile, if other audience have any doubt, any query,
Yeah, sure. You
please,
can ask. Yeah.
please ask.
So I am loading the project. Is there any questions that I should attend? Any questions? Okay, then I am continuing with the projects. It is downloads. Let's say package. It's the already created file. I am loading the microstructure file. And I believe the same project is already shared with you, so you can also load it. Go to the microstructure. Just press on show results because we have already launched the console and everything is done. So it will redirect you directly to the PravaView mode. Well, we ran for a low fidelity, so you can see the grains are not as evolved as in the previous slides that I have shown you because of the lower fidelity. So the computation time here is pretty much low. So you get the microstructure, and I will show you how you can process it. Just click on here. You can see here there are certain tabs. So just clip it, like it's like you are taking the different sections. So I clip it for Z. Along Z, I will take it. I will be clipping this file. So it will be apply. So oops, it is gone. With this view also you can see how the grain growth, the laser tracking can be seen. You can see how amazing it is to see that the grains, the laser tracks, they have merged with each other. Then this band is particularly having the equiax sort of grains, that is the merging of the columnar fronts. And we can see here, let's make it a little bit more interacting. um, let's go for the Y section. Okay, let's not do this. Let's do this side, and I want to see from that side. Yep. So we can see here how the grains, we can see it from a different section. We can change this orientations from this. So we just cut the entire microstructure pool for a single layer, and we just cut it and show it for different orientations, for different aspects. We can show it here. We can take different slices for different temporal temporal evolutions. Let's say I am taking one slice for this section. Let's say I am taking it near the boundaries. So what would be the difference? So the difference is the columnar fronts will change. They will, from this section it will be appeared, it is across the building direction. So what you can see here will be the initiation of the columnar fronts. That would be this section, or this particular slice will be. So I am showing you that. Okay, you see it's a single slice. It's like a pizza slice that you can see here. Single slice. You can see it quite efficiently. Yep. So see it here. So it's there. It's a great piece actually, that you can see the entire temporal evolution here. Once you have different slices, you can merge them and you can have an entire, like a story play. You can turn it on, turn it off, and you can do with anything with the PravaH software. You can regain the entire structure, you can regain it. So that's how it can be operated. And another aspect of it, I would like to, for the further processing, I would like to show you. And you can also even cut the sections based on your need. Like let's say you want to see it like this. It's very interesting, and you can explore it, and it can give you, you see how it is getting evolved from this section, from that section. It can give you the n number of views. It's very interesting. And let's say we clicked on this. There is already one tab, that is analyze microstructure. Let's analyze it, and from that we can calculate the grain size. You know, grain size is pretty much important in additive manufacturing, not just additive manufacturing, for the microstructure analysis. Yeah. So calculate grain size. I pressed it. It will take a while, and you can check it on the, well, it's showing that there is an error for the grain size calculations. Check. Okay, grain size is already done here. Yeah. So grain size is already here. So what we can see, this is the grain size distribution that you can collect from the results, or you can collect from the same location that you have. So this is the grain size that we have calculated, that we have collected from the same software. I guess I should get back to, because we are running out of time. Another interesting session is waiting for you. And yeah, so let's get back to the simulation part. Sorry. Is the screen entirely visible? Are we? Yep. So yeah, you can see here after you proceed with what I am doing now. So this is the microstructure that I have shown, that I have demonstrated to working on. And this is the second microstructure that is observed based on the different conditions that your previous session has already discussed about. I have simulated with the entire microstructure, and yeah, they are all in lower fidelities. So you can see here at lower fidelities, the microstructure can be like this, but yeah, with more computation times, it can be improved significantly, that I have previously shown you in the microstructure. Coming to the strengthening components, because it is one of the most essential part of it, that is the part qualification, that is whether the material, whether it is even possible or not. So we don't even need to have all the data. So what you can have, that you can get some idea from the solution, solid solution strengthening, that is the based on the chemistry of the material. We can have the grain size based strengthening, that is from the Hall-Page equation. We also have the Taylor strengthening, that is the dislocation density, because dislocation density in additive manufacturing is typically high, that is in the order of 10 to the power 15. Considering these parameters from the literature, and we can see that the dislocation density is in the range of 184 MPa. The strength due to solid solution is pretty much less, which is quite common, and that is because of the constitutional segregations. Apart from that, even like along with the synergy with the experimentation, we can also add other components, that is the precipitation hardening, and these are not covered in this length scale of the simulations, of course. For that you need different sorts of simulation to get the precipitation and all that. That is computationally challenging. So I'm providing a easier pathway, and that's why using these three different components also you can estimate the strength. So we can see the grain size, since the grain size is pretty much same, what I have seen here. So it is in the similar sort of order. So we can see that it's a similar sort of strength that we are getting. Coming to the another aspect of additive manufacturing, that why are we actually doing this exercise at all? I mean, we are our main intention should be that whether we can explore new materials with the aid of simulation. We need to have a larger data set. We need to have a larger scope, so that we can cover the entire materials regime. That is, we can explore new alloys, because we know that in additive manufacturing, specifically in the laser powder bed fusion, the number of alloys are pretty much less. So to enhance that data set, we need to generate data. For that data, we can use simulations, and also these data is very essential, specifically for the defect mitigations and the defect analysis purposes. You can see here how the porosity, non-uniform melting, and lack of fusion voids can altogether form for a parameter that let's say we haven't optimized for. So consider this, the entire exercise you are following for an experiment. Can you imagine that how many number of trials we need to do? Can you imagine that what charges we need to pay for all these experimental analysis, the time slots, and pretty much everything is quite challenging, even in this country and even in other countries as well. So to get rid of that, simulation can be a better tool, so that after you have an optimized microstructure, you know the optimized parameters, just print it, try it, print it, and just do the microscopy, and you will get the entire thing. So here I am proposing a new alloy, that is CMSX4, and it is quite a new these days, and people are exploring this alloy so far. And it is a potential alloy for the aerospace applications. It's a nickel-based super alloy, like similar to that of Inconel. And we can see here that some of the researchers have been already working on this one, and these are some of the images from that. So this is also a nickel-based alloy. It also has precipitation hardening and dense dislocation networks, because it's additively manufactured, and it has a stable at high temperature. It is stable phases at high temperature as well, similar to Inconel, and it has great creep and fatigue resistance. So my take on this particular thing will be, in combination with a simulation and experimental data, which is actually helping you for the part qualification. That is, you can propose a material for aerospace grade material. Without the aid of simulation, the entire process will be tedious, time consuming and inefficient as well. With the aid of a simulation tool, specifically to physics informed tool like PravaH, it will actually help you to it is actually giving you the leverage of using these techniques and using the in synergy with the experimental data. You can create that data set. So okay, I am showing you how exactly PravaH is assisting in the part qualification. That is, it is covering an end-to-end solution, that is the particle dynamics, molecular dynamics, and microstructure analysis, which I have also covered just now. It will also provide you a complementary approach for the, you can say, with the experimental, and you can also predict the variation in the microstructure based on different solid liquid interactions, because you have the CFD data imported on that. It reduces the material wastage quite effectively, that I have already discussed. If you reduce the number of trials, you need less powder, you need less experimentation, so the overall cost of the entire process cycle will reduce drastically, reducing the direct reliance on the microscopy. You can, or let's say the other characterizations, if you take one material, you do some combinations and you just let it try, which is commercially expensive and the industries find it pretty much challenging. So with the software you can do that much better. It will actually augment you with the different material combinations. So the better microstructure understanding will help, or rather the physics informed tools will actually help you to have a scientifically assisted material design, and you can have that effect. With the PravaH, I would like to show you a little bit more on that aspect. Let's say I am doing it for a new project. Let's say I'm create new. Let's say I am doing a create project. Let's say CSM X4. I want to try for I'm putting my initials and okay, create new. I put it here only. So now we have the microstructure, and go to the settings. I have shown you and discussed what these parameters can do. For alloy, you have these letters, and we can see that we don't have CFS4. Okay, then what are we gonna do? We can go for new alloy material. So we can just select create a new alloy. And okay, and you can see in the macro scale tab we are putting a new alloy, that is, let's say the name it CSM, create a new alloy, and the name, save the alloy as CSX4, and we can see we can put the process parameters. You can have the process parameters. I sent you the assignment questions, and just check on the process parameters of CSMX4 from here. So here you have the chemistry of it, you have the molecular mass and everything. Let's just copy it. Mass, this, sorry. And we can have the densities, and we can put the densities from here, from this chart. The concerned data is taken from literatures, and you can put all these temperature dependent densities here. You just like this, just put, let's say we start with 1660 kelvins, and the values will be 7720. that's how we do it. And you just need to go through all this exercise. You just put all these temperature dependent properties here in this from this same set, and you can change the emissivity. It is 0.08 for the solid. For the liquid it is different, it is 0.04, and then you just need to change it accordingly. For the solid liquid Lee constant, these Lee constants and the other constants you need to check on. You need to, for the calibration purposes, you need to go through that exercise. And yeah, pretty much like this you can enter a new material and carry on the same exercise that I have shown you in the slides. Sorry. Yeah. So the same activity you need to take on with I have also put this particular activity as a part of your assignment, and you can carry on with that. You can enjoy with the software and play with different parameters, optimize it for CSMX4, and get it qualified for an aerospace applications. And yeah. So I would like to acknowledge my other team members who are working with me. They are doing a remarkable job, and we are leveraging the entire additive manufacturing process as a whole, I believe, because we are importing a simulation based solution for the process. Now I would like to, for the next session, I would like to call Mr. Mateen Ahmed, and he will be discussing the aspects of AI into this particular thing. So importing AI in the large data set you will be generating, and using AI assisted tools, you can augment a new dimension for the material selection, material processing for this software. So that's all from my end.